David Smith here with another Flipped Classroom math video. A few tips before we get started. Remember, you can always pause the video to make extra notes or write down questions for when we meet in class. Also, remember to pause the video when I provide an example. Work that problem, then start the video up again and see how well you did. You can also turn on the captions so you can see my words written below on the screen. You can also speed up or slow down the video if you wish. Remember to think hard, follow along, and bring your best brain to the next time we have class. In today's lesson, we're going to mess around with derivatives using e, the natural log, sine, and cosine. So we're going to warm up with 3 problems that has us take various derivatives with these 4 types of functions. That'll be kind of a warm up, nothing new there, just a little bit more practice. And then we're going to do a 4th example where we're going to actually do quite a bit of work with a trigonometric function. We're going to use all the tools that we did in our derivation chapter, first and second derivatives, to figure out the information about that function so that we can then graph that. And that's going to be new, so you want to buckle your seatbelt, take good notes for that. But first, let's start with a fairly straightforward one. F of x is 3e to the 5x plus sine of 2x minus 7. Go ahead, pause the video, use what you already know, and let's get f prime of x up on the board. Okay, so with e, remember, the derivative of e to the x, super simple one. Now when we have a 5 in there, that 5 gets multiplied by our coefficient here, but the e to the 5x stays the same. So we took our 5, multiplied it by our 3, so we get 15e to the 5x. So that's our first derivative, or the derivative of our first term. And then sine of 2x minus 7, first we take the derivative of the outside of the function. This is a chain rule problem, so that becomes cosine 2x minus 7, and then we multiply that by the derivative of the inside. So 2x minus 7, derivative there is just 2, so I put my 2 out here. So here is my derivative function for our first problem. All right, go ahead and try this one. We've got y equals cosine x times the natural log of x. And before I turn you loose, this is a product rule, so you might want to remember how your product rule works and then give it a shot. Okay, so I took it a few steps for you. I still want you to see if you can finish this. So remember, we have to use our u's and our v's, product rule. So u of x is our cosine x, u prime of x is our derivative of cosine, which is minus sine, and then v is our natural log of x, and v prime is 1 over x. So the product rule says y prime is going to be u prime of x times v of x plus v prime of x times u of x. So go ahead and pause the video, do your plug-in step, and reduce that down. Okay, there's not too much to this one. My plug-in step here, I've just plugged in my various functions from here into the formula for the product rule, and really the only simplification I could do is do 1 over x times cosine x is just cosine x over x. So there you have it. Our last warm-up. G of x is cosine of the natural log of x. So I'm not going to give you any more specific prompting. I want you to pause the video and find the derivative of that function. Okay, chain rule problem. Derivative of the outside. That would be cosine of something. Cosine of ln of the natural log of x. So we get minus sine of the natural log of x times the derivative of the inside. The derivative of the natural log is 1 over x. So that's my next step. I simplified it only slightly. These are very much equivalent answers, but I like my fractions to be more compact. So this is minus sine natural log of x over x. All right, let's begin our longer problem for this lesson. So here's our initial prompt. Consider f of x is cosine x minus sine x. So pretty simple trig function. We just have our 2 functions, cosine and sine, and we're subtracting sine x from cosine x. So you might think about what that would look like on a graph, because that's where we're going. We're going to go all the way through the steps so that we can sketch a graph. So that should tell you that this is probably a paper 1 or a no calculator type of question. Finally, over the interval 0 to 2 pi. So we don't have a big long interval, we're just going to 2 pi. And you can tell we don't have any multipliers on our period, so 0 to 2 pi is going to capture the full range of our function. Okay, so I'm going to walk you through this in a certain order of steps to get all the points we need to make our graph. First one, Find the x and the y intercepts. So you want to think about that for a minute. What happens at the intercepts? Good question. At the x-intercept, y equals 0, and at the y-intercept, x equals 0. So take that understanding, and let's do this step by step. Let's find the x-intercepts first. So that's where y is 0. Let me take you a little further. So I set my equation equal to 0, y, that's the f of x part of our function, right there. And this has to equal 0. So cosine x minus sine x should equal 0. So let's take another step here. Let's add sine x to both sides. So now we know we have our x-intercepts when sine x is equal to cosine x. So think for a minute about where that happens, because it happens at a very specific, or actually 2 spots in our range from 0 to 2 pi. What you might do is sketch a real quick unit circle just so you can see that nice and clear. Okay, unit circle time. Here we go. If you'll remember that at our 45 degrees, which is pi over 4, that's where our x and our y are the same. And x and y both equal 1/2. So our first place where x and y are the same is at pi over 4. So from this little equation we made here, that means that we have an intercept at pi over 4. Or I should say, an x-intercept at pi over 4. Now remember, we count around the unit circle in 45s by pi over 4. So 1 pi over 4, 2 pi over 4, that's just pi over 2. 3 pi over 4, 4 pi over 4, that's just pi. So to get to the next 45, we're at 5 pi over 4. And at that point, cosine and sine are also equal. They equal -1/2. So that's our second x-intercept. 5 pi over 4. All right, let's take a look at the y-intercepts. Remember, the y-intercept happens when x is 0. So the equation we're solving here is f of 0. So I just put in 0 for x in my function. So I have cosine 0 minus sine 0. Now again, if you totally have the unit circle in your brain, you don't need to draw it. We've got cosine 0. That means we haven't gone anywhere. So the cosine here is 1. We haven't started going back where cosine gets a little smaller than 1. So cosine 0 is 1. Sine 0, again, that's the y direction. So when we're right there, we're neither positive or negative. Sine 0 is 0. So we have 1 minus 0, or 1. So our y-intercept is the point 0, 1. Okay, I've prepared a bunch of things. I'm just going to walk you through that. So, number 2, find the intervals where f of x is either increasing or decreasing, and find the maximums and the minimums for that interval. So what we're going to try to do is figure out what our function is doing. So we need this information to be able to make our function graph. So the first thing, if you recall from our derivative unit, what we need to do is find the derivative of our function so that we can then use it to find out where the function is increasing or decreasing. Because remember, the derivative gives you the slope of the tangent line. If the slope is positive, function increasing. Slope 0, min or max. Slope negative, function decreasing. So we're going to go through all that. So first step, we need to find the derivative of our function. So I went ahead and did that for you. Here's our function. So the derivative is just minus sine x minus cosine x. Okay, next step, what we do, we need to find the places, the turning points, the mids and the max, where it changes from increasing to decreasing. So the way we do that is we set the derivative function equal to 0 and then try to look at those points, solve for them. So here's our function, minus sine x minus cosine x equals 0. So when we move cosine over to the other side, I get minus sine x equals cosine x. So those are the places. When this is true, we have a tangent line slope of 0. So this is very similar to when we found the tangent line slope for our intercepts on the last board, except now we're finding mids and maxes on our function. So check this one out. When negative sine equals positive cosine, we're here and here. We're at 3 pi over 4 and 7 pi over 4. And the way that works is at 3 pi over 4, cosine is -1/2 and sine is +1/2. So that satisfies that equation there. And the same thing here, where cosine is positive 1/2, but sine is negative 1/2. Really, the way to see this is that sine and cosine have to have opposite signs but be equal. So there's only two places on the unit circle. That's here and here. So what I did is I came back to this mark here. This is our continuum from 0 to 2 pi. Remember, that's our range that we're looking at that we need to make our sketch for. And I marked my important points, my 3 pi over 4 and my 7 pi over 4. This is not to scale, but it is going to give us the ability to figure out where the function is increasing, decreasing, and where the mins and the maxes are. Okay, so the next step is sort of a testing step. We just need to pick values inside of each range and test whether or not the derivative function is negative or positive. We already know where the derivative function is 0. That's at these 2 points. But now we need to test something else. So always pick an easy one to do. So what I did is I picked 90 degrees, or pi over 2, and I plugged that into f prime, my derivative function. And at 90 degrees, sine is 1, so I have a -1, -0. That's what cosine is at 90 degrees, that's 0. So the answer is -1, which is negative. So I know that my function is negative here, so I can start to sketch that in. And I know that means I'm going to have a minimum here at 3 pi over 4. Now what I want you to do is pick two values for here and test those ranges, make sure and confirm what the derivative function is doing at that point. Okay, so two more. I picked pi because that's right in between, super simple. So minus sine of pi is 0, so that goes there. Cosine of pi is -1, but we have a minus -1, so that makes that interval positive. So we're positive here, so our curve goes back up. Now, we're almost certain that we're going to go back down here. It is a turning point. The derivative is 0, slope of tangent line is 0. But just for thoroughness, I went ahead and calculated that, and I realized that popping over here to our unit circle, here's 7 pi over 4. That's where that's our turning point. So I went ahead to basically 330 degrees, or 11 pi over 6. My values there, cosine is √3 over 2, sine is -1 over √2. So I plug those into my formula there, and I get a negative number. So that means that we're negative here, and we go back down. So last thing for you to do here, we want to state the interval where the function is increasing or decreasing. So you have interval notation already, so I'm just going to put that right there. Go ahead, find a spot in your notes, pause the video, and do that. All right, let's wrap up step 2. Here are my intervals. It's increasing from 3 pi over 4 to 7 pi over 4. Makes sense from our graph here. It's decreasing over 2 different intervals, from 0 to 3 pi over 4 and from 7 pi over 4 to 2 pi. And then judging from our graph, that makes this one a minimum and this a maximum. Second derivative time, woohoo! So prompt 3 here, find the intervals where f of x is concave up and concave down. And if you remember from our chapter on derivatives, that's exactly what the second derivative will tell us. So first step, find the second derivative. Here's our original function. I go ahead and transferred the first derivative up here for your reference. Go ahead, pause the video, quickly give us the second derivative. Okay, so here we go. I just took the derivative of the first, gave me the second derivative, which is now minus cosine x plus sine x. Now, we need to find the points where the graph switches from concave up to concave down. And that's where this derivative is 0. So go ahead, set this derivative equal to 0, solve it, and find the intervals, or find the turning points of concavity. Okay, so I set them equal to each other. I didn't set them equal to each other. I set them equal to 0, and I moved cosine over to the other side of the equation so it became positive. So here is my solution, where we have a turning point where the slope of the tangent line on the derivative function is 0. Okay, so that's where cosine and sine are equal. So that goes all the way back to our first step. That happens at pi over 4 and at 5 pi over 4. So here is your number line where you use to chart concavity. So go ahead, pause the video, Figure out where the second derivative is positive and negative, and figure out your mins and your maxes so that ultimately we can figure out the intervals where f of x is concave up and concave down. All right, so I had to plug in 3 values to figure out my concavity. There's the result from that. I just picked my first one. I took the second derivative of pi over 6. That's in between here. That's 30 degrees on the unit circle. And I remember that the cosine is root 3 over 2. I got a negative minus root 3 over 2 plus 1 over root 2. That's going to be a negative number. So I have my negative. My line is coming down. That's going to tell me I have a minimum here at pi over 4. That's where it switches concavity from concave down to concave up, as shown by testing this one with pi, because that's right in between these two numbers. So at the second derivative of pi is just going to be 1. That's cosine. Pi at pi, cosine is -1, but I have a negative out there. So that becomes 1 plus 0, which is sine at pi. So that's positive. So now we're coming up. That means we have a maximum there. And then finally, I checked it at 3 pi over 2. That's 270. That's just past here. So that's in this interval. At 3 pi over 2 at 270, sine is 0 and cosine is -1. I'm sorry, cosine is 0 and sine is -1. So overall, the sine, S-I-G-N, of our function is negative. So we have it concave down. So that gives us our intervals here. So we know that the function is concave up from 0 to pi over 4. I'm sorry, concave down from 0 to pi over 4. Concave up from pi over 4 to 5 pi over 4. And then again, concave down from 5 pi over 4 to 2 pi. Woohoo! Now we're ready to make a sketch. Okay, here we are at our sketch point. Now I've put a lot of stuff on the board before I actually draw my curve in. So I put my axes here. This is my f of x, this is my x. I've scaled it from 0 to 2 pi. That's the interval over which we are concerned. And then over here I summarized everything that we figured out from those last boards. So my x-intercepts, my y-intercept, and my mins and my maxes. Now I need to tell you here that to get the y value, I plugged the x value, these two values, into the function, into this function, to get the y values. So we're going to need those because we do need to plot the min and the max, and we do need the y value for that. And then the rest is just a summary of the previous boards. Here's where the function is increasing, this one interval. It's decreasing over these two intervals. And then here it's concave up over this one interval and concave down over that interval. So a point we didn't mention in the last board when we talked about concave up and down, the mins and maxes on those graphs are inflection points. So those are where the function changes from concave down to concave up. So, okay, so now as a graphing aid, I've marked a couple things on here. I marked the intervals over which it's increasing and decreasing, and I've marked the intervals over which it's concave up and concave down. So this is going to help us sketch in our graph. Finally, I marked my intervals on my axis in increments of 45 because that captures all of our essential points. Okay, so if you want to get that into your notes, then what I'd love for you to do is pause the video and see if you can sketch in the function. You might try pencil, so you could erase if you like, but go ahead and do just that. All right, let's show you a little bit more before we get our curve in there. So what I did is I marked the key points that I know. My y-intercept, my x-intercept, my minimum here, which is that right there, the 3 pi over 4 minus root 2. Remember, minus root 2 is about 1.4, so that's not quite to 2, so that's about right for that. Then again, my x-intercept at 5 pi over 4. Apologies, I wrote 5 pi over 4 on the last board, so I changed it. That is a 7 pi over 4. So I went ahead and marked that maximum at 7 pi over 4. So now I can pretty much sketch my graph. So go ahead and pause the video and do just that. Okay, we're at the end of it. Check this out. I'm coming down here. I'm decreasing over this interval. Makes sense, I'm decreasing. So, and then I change to increasing over this interval all the way up to there, increasing to the max, and then I'm decreasing over this last interval from 7 pi over 4 to 2 pi. So the increasing, decreasing, that works, that maps to my graph. Secondly, my concavity. Remember, the function is concave down here. Even though it's decreasing, it's down. But here is an inflection point. Now it's concave up. So it's still decreasing, but now the curve is focused on up. In fact, it's going to be concave up all the way up here to this intercept where it changes to concave down over that interval. So this example really summarizes everything we did with graphing and first and second derivatives back in our derivative chapter. So lots of stuff here. I know this was a long video. I really appreciate you riding along with me. If you still have questions, write them down now and bring them to our next class. You can also watch the video again and perfect your notes. Finally, if you enjoyed watching my video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.